Okay, so just now we have done with what we call as MPL circuit law, and I have done one application that is magnetic field due to a long, infinitely long straight current wire. We have done it, and then now what I'm going to do is I'm going to do a solenoid, finding out magnetic field due to a solenoid. And first, before I do a solenoid, let me define what exactly solenoid is, what exactly solenoid looks like. So this is the diagram. This is the pictures of solenoid. So you will get a solenoid. A solenoid normally consists of insulating. This is insulating wires. You require long insulating wires, and then wind, right? Closely wound in the form of helix, right? These all are in the form of helix. It is something like this, right? It is something like this. And these things are wound closely, right? It's closely packed. Right? This distance is going to be extremely very small. Distance is extremely very small, right? So solenoid consists of an insulating long wire closely wound in the form of helix, right? In the form of helix. However, look at here. However, since the distance between the two neighboring turns are very, very small, so they can be regarded as a circular current loop. They can be regarded as a circular current loop. That you should keep in mind. Very, very important, right? So, since the distance between the two neighboring turns are very, very close, very, very small. So therefore, each circular loop, each turn can be treated as circular current loops. Circular loop. That you should keep in mind, right? So this is the example. This is the definition of solenoid. So I have this diagram is this, and a few diagrams I have. Again, this is a solenoid. Again, this is a solenoid. Now, if I have if I let the current to pass through a solenoid, this gives you a magnetic field. This gives you a magnetic field, right? So the main purpose is to find out magnetic field inside solenoid. Main purpose is to find out magnetic field inside solenoids. So whenever we discuss a solenoid, you should have two important points, right? One thing is that number of turn per unit length. This is N is what we call as number of turn per unit length should be very high. Number of turn per unit length should be very high, and then length of solenoid has to be comparatively longer compared to length of solenoid must be longer than a radius of solenoid. Now that these few conditions should satisfy. If these conditions are satisfied, then what we have is magnetic field inside solenoid is uniform. Field inside solenoid is uniform, and field lines are the straights. Field line are straight, parallel to each others. All right, straight, parallel to each others. All right. And one more very important, right, under these conditions, magnetic field outside solenoid, magnetic field outside solenoid is zero. Outside in a sense this. Alright. We consider that magnetic field outside solenoid is zero. This magnetic field outside solenoid. Alright. Magnetic field outside solenoid is zero, right? Magnetic field outside solenoid is zero. So this condition should satisfy. Now here I have one more diagram of solenoid. This is two-dimensional nice diagram. This is output. Look at here. current goes out and goes in. This is how current goes like this. And the direction of magnetic field is again given by right hand thumb rule, right? Direction is given by right hand thumb rule. So look at here, this is how it goes. Currents coming out, right? Currents are coming out, goes into this, so this is magnetic field. So these are the field, right? Magnetic field, and this is almost parallel, right? Almost parallel. Then I say magnetic field outside is going to be 0, right? This is almost 0. So idle solenoid. And look at here. Now, one more information I would like to give you here is there is this magnetic field, right? I have every turn, right? Every wire magnetic field cancel each others. So the space is very small. However, there is some space. This magnetic field direction is in this directions, and magnetic field due to this current wire is in these directions. Magnetic field due to that current wire in this. So these two cancel each others. These two cancel each other, these two cancel each other, these two cancel each other. So overall, magnetic field between wires are always 0. Magnetic field between wires are always 0. Very simple, right? This all the magnetic loops are opposite each other. So these two magnetic field cancel each other. So therefore, there is no magnetic field between two current wires, right? So that you should keep in mind. This is the diagram. Alright. So we say that magnetic field outside solenoid is 0 for idle solenoid, and magnetic field inside solenoid is parallel and uniform. So this is the diagram, right? So now what I am going to do is I am going to find out magnetic field inside solenoid. Magnetic field inside solenoid having those condition, right? So I'm going to use Ampere circuit law. So this is the diagram I have. This is the again magnetic fields are coming out, currents are coming out, goes into this. This is how it gets into this. So it is like this. Currents are like this. Look at here. This is coming out of planes. I write here out of plane into the planes, out of the plane into the planes, and this is how it has. This is how it has. So now what I'm going to do is I'm going to find out magnetic field inside solenoid. So I'm going to take Ampere circular loop. I'm going to take this loop, Ampere loops. All right. Let us take AB Ampere loops, Ampere loop A, B, C, D, A. This is Ampere loops, and this loop is divided into 4 parts. All right. So loop, I am going to take this BC part, length. This loop has a 4 length BC, look at here, length BC is, I just write here, BC is perpendicular to magnetic field. Alright, length BC is perpendicular to magnetic field, so therefore magnetic field is going to be 0, right? So magnetic field along BC is going to become 0. No contribution from this loops, this length. Now next length I'm going to take is CG. Alright. So since the CG is length CG is outside, since this is outside solenoid, since this is outside solenoid, again magnetic field becomes 0, right? 0, right? Outside solenoid, magnetic field must be 0. Now I am going to take a length DA, Again, DA is perpendicular to B. Alright, hence B along DA is going to be 0. So B along, right? B along BC is 0, B along CD is 0, y goes outside, and B along DA is 0, right? Hence, I write here B along GA is 0. Now finally I am going to take length. Let us take length AB. Let us take AB. Length AB, let's say I say length AB is along B. Length AB is along B. Now I am going to use the Ampere law. What is that Ampere law? Before that, I will write here big Ampere law, right? Let's do this before. This is the total current, right? I just say total current or total current penetrating across the surface. So now this becomes a 0. Why? Because 90 degree is 0. So magnetic field along a length BC is 0. Outside magnetic field, therefore magnetic field along a length what is that? CD is 0. Again, this perpendicular magnetic field along DA is 0. Now magnetic field along AB is going to be on this. So B, since along, therefore it is going to become a 1. Cos 0 is 1, and the length is L. Let's say length is L, which is equal to mu naught total current, right? Mu naught total current. Okay. Now look at here, V L mu naught I total. Look at here. So what is I total, right? I total is going to become what is the total current penetrating through the surface? This surface. What is the total current penetrating through the surface? So what is the total current penetrating through the surface? This all current 1, 2, 3, 4, 5, so on, right? So on. So that is going to be, let's say I have n number of turns. N number of turns across this land. If there are n number of turns across this land, the total current is going to become n into by I. I. Alright, I is the current passing through a wire. What is the total current passing through this surface? Passing through this surface is number of turn enclosed by this surface, and number of turn enclosed by this surface is n. So therefore total turn is going to become this. Total current is going to become this. So I write here mu naught and I. Then this goes to denominator. Mu naught N I divided by L. Now look at here. What is N by L? Is number of turn per unit length. So finally I write magnetic field is equal to N I. What is small n? Number of turn per unit length. So this is the magnetic field inside solenoid. This is the magnetic field inside solenoid. This is the magnetic field inside solenoids. So therefore magnetic field inside solenoid is going to become magnetic field inside solenoid is mu naught and I. And mu naught is magnetic permeability in vacuums. N is the number of turn per unit length. I is the current passing through a wire. So this is the final answer. This is the final answer. And what about the direction of magnetic field? Right in thumb. Again, right in thumb. Right? The finger curls. Direction of a finger is curved current, and the direction of thumb is magnetic field. Right. So this is a current. And this is magnetic fields. This is the current and that is magnetic fields. Okay. Alright, so this is for solenoid. This is for solenoid. Now next I would like to do is for toroid. Next I would like to do is for toroid. So for toroid, very similar to solenoid. Only difference is that in case of toroids, it is a hollow circular ring. Alright, it is a hollow circular ring. How are you going to obtain hollow circular ring? Is simple. I am going to join the two ends of solenoid. If we could join two ends of solenoid, we will obtain what we call as toroid. Alright, so toroid. So toroid is what we define as toroid is a hollow circular ring on which a large number of turns of wires are closely wound. Again, simple, right? So this is a one wire, this is another wire. I just wound on a hollow circular ring. I just wound a wire on a hollow circular rings where the neighboring wires are very, very close. So it is something like I have a solenoid and join solenoid two ends. If we join the two ends of solenoid, what we get is what we call as toroid. So this is, so now again what I am going to do is I am going to find out magnetic field due to toroid. So we are going to do three things, right? First, I would like to find out at Q what is magnetic field at Q, and what is magnetic field at P, and finally what is magnetic field inside. Alright. So we are going to point three positions. And what is magnetic field at Q? What is magnetic field at P? And what is magnetic field inside hollow or circular ring, right? Hollow circular ring. This is what we are going to do. And again we are going to apply Ampere circular law. Again we are going to apply Ampere circular law. So this is what I have. This is what I have. So I have. So just now I told you that we have find out three different positions. One is Q. One is Q, that is outside, and another one is P. All right. I hope you could see P, and another one is S. Alright. So for that, what I'm going to do is I'm going to take three circular loops. Three circular loops. This is the first circular loop, second circular loop, third circular loops. This is what I'm going to do. So first point at Q. First point at Q. So point at Q, I have drawn an Amperian loop. Alright. I have drawn an Amperian loops. Amperian loop, look at here, very simple. Amperian loop of radius 3. And what I'm going to do is, I'm going to put a surface. I'm going to put a plane surface. Alright. Surface, let's say I'm going to take this surface. This is the surface. This is the surface. I hope you can see this. This is the surface. Alright. And what we are going to see is what is the current, what is the net current passing through this surface, right? So now I'm going to use Amperian law. Amperian, this is what I have. Let's say net current. And say this referred to net current passing through surface. This is net current passing through a surface. So this is surface Q. Surface Q is current sense. Look at here. This is coming out of plane and this is going into the planes. So look at here, since this surface includes both the current that is going into the plane and coming out of the planes. Alright, I say since the surface enclosed currents, alright, that is both into the surface and out of surface. Alright, therefore what is the answer, right? What is net current, right? Therefore net current is 0. So this is going to become 0. L is non-zero. This is non-zero, right? Since L is non-zero, why? Because this is length. Length can't be 0, right? This is non-zero. Since L is non-zero, so what is going to become 0? B is going to become 0. Alright, this is one case. So magnetic field at the point P is point Q 0. Magnetic field at point Q 0, right? Now what about at point at P? I have Amperian loop, again Amperian loop of radius. What is that? R1, right? Now look at here. Look at it. This, I'm going to choose this surface. I'm going to put this. And you will see that there is no current penetrating into the surface. Since the surface is the most inner, so there is no current either in the plane is not penetrating or out of the plane is not penetrating. So therefore, I is going to become 0. If I is going to become 0, then BL is going to become 0. Again, since L is not 0, therefore B is going to become 0. This is second case. Alright. Now third one, right? Now third one, that is point S. Now third one, that is point S. Point S. Point S. I'm going to take this surface. Surface, I'm going to take this. This is the surface. Now, again, I'm going to use Ampere law. Net current, right? Whatever, right? So look at here. This is out of this plane. These currents are out of this plane. There is a net current penetrating through a surface. There are a net current penetrating through a surface. And how much is that net current, right? I just say net current is equal to number of turn into a current in a wire. Net current is equal to number of turn divided by current in a wire, right? So therefore again B, this is L is the length of a circular loop, and mu naught N I. So B is going to become mu naught N I divided by L. So B is equal to become mu naught N I. So this is magnetic field inside toroid. Magnetic field inside toroid. So this is magnetic field at S. That is inside toroid. That is inside toroid. That is inside toroid. So this is very similar to, this is exactly same as a solenoid. Alright. Okay, this is all about a toroid. Now I would like to do a last topic. Alright, that is forces between two parallel current wire. And the objective of this topic is to define what is 1 ampere. Alright. This was done by ampere, so therefore the unit of current was given after ampere. So the unit of current is nothing but ampere, and how much is 1 ampere is defined by this. So let's see here. I have a long current wires. I have a long current wire. Let's say a long current wire. Long current wire. I say a long 2 current wire. Long 2 current wire. Alright. And having a current IA and IB, and separated by a distance. And separated by a distance, separated by a distance, separated by a distance D, separated by a distance D. Now look at here, since this current wire A has a current, it will produce a magnetic field. Since the wire B has current, B also produce a magnetic field. Because of which, 2 wire exerting force on each other. A force could be a repulsion, force could be attractions, right? But overall, you will find a force exerting on each others. That's the main concept here, right? So now I would like to find out magnetic field due to a current wire A at a point along B. All right, magnetic field due to A. Magnetic field due to A at points along wire B. Alright, and since distance is D, so now we know that what we know is magnetic field due to infinitely long straight current wire. Since this current is wire is long, I can take this, right? So this equation can be written like this: I 2 pi R, since R is going to become G, and this is A. And then what about magnetic field magnetic field due to B at a point along wire A? Look at here. This is going to become mu naught current B 2 pi D. Alright, so now let's see the directions. Look at here. Direction is given by right hand thumb rule. Direction is given by right hand thumb rule. This is what I have. So magnetic field here, this case magnetic field is downward. Alright, this magnetic field is downward. Alright, this magnetic field is downward. What about that magnetic field? Look at here, upward. Right, magnetic field is, this is directions. Magnetic field is, one is upward and another one is downward. That's what. Now what I would like to find is the force. Alright, so the point is, what is the force? This is the force on, this is the force on wire B due to current in wire A. Force on wire B due to current in wire A. Current in wire A. Alright. That is force on a wire B due to a magnetic field due to current wire A. That's the simple, right? So this is going to become IB L, some L length, alright, and B is going to become BA, right? Magnetic field is due to this here in this case magnetic field is due to current wire, right? This is magnetic field is due to current wire A, so therefore I have written BA. Alright, now this is what I have. IBL. What is this? This is B naught IA divided by 2 pi D, and this is the force on a wire B due to current in wire A. Or this, again I say this is the force on a wire B due to a magnetic field, due to wire A, right? This is the force on a wire B due to current in a wire A. And now let's find out the directions. Let's find out the directions. The direction is given by right hand thumb rule. So look at here. This is the current. This is the current. Current is along these directions. And what about direction of magnetic field? Magnetic field is downward. So downward. So this is the direction of currents. So direction is again I'm repeating, this is the current wire, this is the direction of current, so therefore this is direction of L, and L cross B. Alright, L cross B, and thumb is the direction of force, L cross B. This is L cross B. B is downward. It is something like this. I have magnetic field like two wire. Wire A, wire B, and magnetic field is downward. Current is this. So this is the direction of magnetic field. Look at here. Alright. Direction is towards A. Now let's talk about force on A due to current in a wire B. Force on A, this is the force on a wire, let's see, a wire A due to current in wire B. Alright. So this is given by again the force. Direction I will tell you later. F is equal to I A L B B. How much is BB? I A, what was force on wire A due to magnetic field of wire B, mu naught IB divided by 2 by D, right? So what is the total force? Total force is equal to total force. This is the total force. And you would like to find out the direction now. Now direction is something like this. Now this is the wire A and this is wire B. This is wire A, this is wire B. And what about magnetic field? Magnetic field is outward and current is in this direction. So look at here. This is direction of length elements and magnetic field is upward. And then direction of magnetic force is this. This is direction of force. Alright. And the direction is towards wire B. So that means you find attractions. Two wire attract each other because of a current in a two wire. Alright. So wire A attracts wire B also attracts wire A. Alright. So therefore what I am going to write here is now and magnitude wise they are same, equal and opposite to. So this is what I have, right? This is exactly same as what we have done in Coulomb's law, right, between the two charges. And this could be either attraction, force could be either attraction or repulsions, right? So that's very simple. And now the point here is, if the direction of currents are along the same directions, look at here, direction of currents are along the same directions, so therefore there is attractions. Now let's see, if a direction of currents are opposite direction, obviously it is going to be repulsion, right? So we will see. So this is how we can get a direction of a current because of a current wire. So I have electric currents, and this is how you get a magnetic field, right? And term is a direction of a currents, and then the curved fingers are the direction of magnetic field, right? Diagram. Alright, this is what I have. Alright, I've shown you this, both attract each other, right? Same directions. Same direction they attract each others. Same direction they attract each others. Alright? Now this is what I have. Opposite directions they repel each other. Look at here. Opposite direction they repel each other. This diagrams no, you can get it a direction of magnetic field also. If it is like this, alright, magnetic field goes like this. This like this, magnetic field goes like this. So this side magnetic field, that side magnetic fields are always opposite, therefore they attract each others. And this side magnetic field and that side magnetic field are always along each other for opposite directions, so they repel each other. Look at here, the magnetic field is like this. Here in this case, magnetic field is like this. So these two magnetic fields are along the same directions, so therefore they repel each other. So diagrams, I have shown you a diagram so you can practice. Alright. So these forces are equal but opposite directions. Alright. And if the two directions are along, or two currents are along the same directions, you find attractions. If the two currents are of opposite directions, so you find repulsions. Now we would like to define, again I have this, right? Okay, you can go and you can do this and get the directions and see where the forces are, right? Y1, Y1. One is parallel, another one is anti-parallel. And now last, that is how to define 1 amperes. How to define 1 amperes. Alright, yes, you may answer right. 1 ampere is defined as 1 coulombs amount of 1 coulomb passing through a unit area in 1 second is going to be 1. Yes, this is 1 ampere, but this is practically not possible to measure it, right? I can't go on and find how much is 1 coulombs, and then I can't see whether it is passing through or not. The simplest way of defining 1 ampere is this, right? So what I have is, I'll be having a 2 wire. I'll be having a 2 wire separated by, let's say I'll be having a 2 wire. Let's say this is the wire. I'll be having a 2 wire. Let's say separated by a distance 1 meter. Separated by distance 1 meter. So this 2, let's say this, right? Separated by a distance 1 meters. And the law says that the 1 ampere says that the force, if the current in the 2 wires are said to be 1 ampere, if the force between 2 wires is going to be this much, right? 2 into 10 to the power minus 7 newtons per meter, right? So this is what I have. All right. So this is how we define, right? So it is said to be 1 ampere. It is said to be 1 ampere passing through these 2 wires, all right, separated by a length, separated by distance 1 meter, if force between a 2 wire is equal to force per unit length. Force per unit length between a 2 wire is equal to 2 into 10 to the power minus 7 Newton per meters. If this is so, then we say it is 1 ampere. If it is 1 into 10 to the power minus 7 Newton per, then this is going to be half ampere, right? So this is how we define 1 ampere. So again, I'm going to define. So it is said to be 1 ampere passing through a 2 wire separated by a distance of 1 meter if the force per unit length on each wire is going to be 2 into 10 to the power minus 7 Newton per meter. If this is so, we call it as 1 ampere, right? So this is the ampere is the value of that steady current which when maintaining each of the two very long straight parallel conductor of negligible cross sections and place 1 meter apart in vacuums would produce on each of these wire a force equal to 2 into 10⁻⁻7 Newton per meter of length. So this is what we define as 1 ampere. So F, this is force per unit length. Alright, force per unit length is going to become, this is same for both, right? IA, IB separated by what is the distance? G, right? This is force per unit length. This is what we define as force per unit length. Okay, so with this I'm going to stop, and now we are left with 2 or 3 topics of this chapter, and hope we'll finish next session, right? Thank you.